One of the most perplexing things about space is black holes. First of all, they aren't physical objects. Rather, they're the product of extremely distorted space-time. As a result of this distortion, some very strange things begin to happen around them, which will alter your view of how the universe works. Some of these anomalies are so outlandish that you might not believe they exist if it weren't for the solid math that supports their existence and properties. And there's growing evidence that this math is. Through observations in our own universe, I, Alex Mullen, and you are watching Azram. In this video, we will delve into the uncharted territory, trying to understand the weird science behind black hole formation, surrounding phenomena, and potential escape mechanisms. I hope that by the end of the video, you'll have earned a subscription and like. Black holes come in various sizes, with the smallest being observed. Black holes range in mass from around 38 solar masses to billions of solar masses. These supermassive black holes have been around for nearly the entire universe's history and are so enormous that their event horizons could encompass the entire solar system. Modern black holes are the last stage of the life cycles of extremely massive stars. When they're born, these stars are essentially balancing under the weight of two forces. There are two forces at work in a star: gravity pulling the mass inward, and the intense pressure that causes hydrogen atoms to fuse into helium. This new, denser element requires less energy than the original two hydrogen atoms did, so the excess energy is released. The second force is the star's outward radiation of heat and light, which acts as a counterforce to gravity. The star will stay mostly unchanged until its hydrogen fuel runs out, at which point it will fuse the newly formed helium into denser materials like carbon, neon, oxygen, and silicon. Then it will start fusing iron, but iron doesn't store energy in its new form, so it has no spare energy to release. Instead, it sits in the star's core, growing larger and larger without any. Like a hammer hitting an anvil, the star's mass rushes down to meet the core with such force that the rebound of that blow is what we call a supernova. Matter and energy are blasted out across the universe from the crackback in one of the largest explosions possible, producing elements even heavier than iron all the way up to a neutron star, a tiny ball of matter no larger than 25 kilometers in diameter and packed with enough mass to equal 1,000,000 Earths, is what remains of a star when its mass and the force of its collapse are too low. On the other hand, if the star's mass and the force are large enough, the laws of physics as we know them collapse, and what we end up with is a black hole. It's important to note that the black sphere you see in an image of a black hole isn't the black hole itself, but rather the result of the stellar collapse. According to scientists, black holes are believed to be even denser and smaller than neutron stars. They are singularities that emit forces that distort space and time. How come we don't know this for sure? It's all due to something called the event horizon. We've known that objects with mass exert gravity since Newton's day, but when Einstein introduced his theory of general relativity in 1915, a colleague of his named. Based on this, K.L. Schwarzschild reasoned that objects so massive could generate such strong gravity that not even massless light photons could escape, let alone light itself. When you look at a black hole in a picture, what you really see is the event horizon, the boundary line where the gravitational pull is so strong that light can no longer escape, and all that remains is darkness. Here's another facet of the cosmos: time. As Einstein said, space and time are inseparably linked. When matter collides with a black hole, it warps space-time around the singularity, which stretches space-time to its limit. At the event horizon, space-time effectively comes to a standstill, creating an intriguing phenomenon for an outside observer looking in from above. When matter gets close to a black hole, it slows down until it stops completely just before the event horizon. After that, there is no more satisfying absorption. Instead, the matter gradually dims until it is no longer visible. When black holes were first proposed, astronomers and physicists weren't sure they existed. It took 40 years for the first evidence of a black hole to be recorded in 1964. Using newly developed X-ray satellites, scientists detected it. In 1970, as telescopes became more advanced, scientists noticed an object in the constellation Cygnus that appeared to be emitting a significant amount of X-rays. They were taken aback because, if it were a star, it would also emit visible light. The object was subsequently designated as Cygnus X1. Based on their calculations, they determined that the invisible object was 15 times more massive than a star. Enormous compared to the Sun, with the densest neutron star having a mass no greater than 3 times that of the Sun, scientists deduced that this was likely the first black hole ever found. Since then, numerous more have been found, with the most massive ones appearing to reside at the galactic centers. In fact, scientists have even managed to capture images of black spots against the whirling accretion disk, which allows for the detection of black holes using X-rays. Black holes don't actually produce any visible electromagnetic radiation. Rather, the X-rays that we see coming from them come from accretion disks, where infalling matter is heated to millions of degrees Celsius by intense friction. Without this infalling matter, black holes wouldn't be visible since there wouldn't be any bright accretion disks to detect them. The study of black holes is an emerging area of physics, and there's a lot more to learn regarding them. Physicist Stephen Hawking postulated in a 1974 paper titled Black Hole Explosions that energy and mass could actually escape from a black hole. To understand this, we need to delve into some very strange theory based on quantum mechanics. But before we get into that, allow me to pose a challenging question. What is nothing? For a second, picture a patch of. If you're familiar with the properties of light, you'll know that light is actually waves of electrical and magnetic charge that are constantly propagating forwards in a straight line. However, let's take a step back and look at the big picture. Space is empty. There are no atoms of space dust inside, and no radiation is passing through it. Can we still say that something fundamental exists here? Look at that word wave. A wave in the ocean is just energy moving through the water. If you look at a single water particle, it doesn't really do much of anything other than spin in a circle. But because it transfers energy to the nearby atoms, that energy keeps moving in a constant motion that eventually reaches the shore. Similarly, a sound wave travels through the air by transferring energy between individual air particles. Each particle moves just a tiny bit, but it gets energized and passes that energy on to the next one. As a photon of light travels through empty space, it hints at a fundamental reality that exists even in nothingness, a fabric that comprises all of reality. Quantum physicists refer to this something as a quantum field. While quantum fields are difficult to understand, they are crucial to comprehending the ultimate fate of a black hole. So, how exactly do quantum fields end? Hawking postulated in his paper that black holes would gradually release energy in small amounts at first, leading to a decrease in the black hole's mass, since energy and mass are synonymous in Einstein's famous E=mc superscript 2 equation. However, as the black hole shrank, the rate of energy release would accelerate, becoming ever faster until, in its final moments of existence, it explodes. Could unleash an enormous energy burst before vanishing forever. However, how is this possible? Since an event horizon is invariably present, how could radiation escape it and trigger such a black hole explosion? The answer is peculiar, and it depends on quantum theory's illogical concepts, which run counter to our everyday reality. If this is correct, then I hope you're ready to find the cosmos to be far stranger than you initially imagined. In order to grasp Hawking's theory, it's helpful to have a basic understanding of quantum fields. Light travels through space like a wave, so even in empty space, there must be some substance for the wave to exist. Scientists refer to this underlying fabric of reality as a quantum field, and they even go so far as to believe that there are multiple quantum fields, all of which overlap and cover every part of the universe, past, present, and future. There is a specific type of something that can be defined by a field. For example, one field could describe all the electrons in the universe, while another could describe the quarks that make up an atom. In this state, the quantum field is relatively quiet, like a guitar string that hasn't been strung or a graph with no value. However, The quantum field is resonating at any point in time and space where mass or energy is present. If you want to know what an electron or a photon is, you need to know that in this theory, the resonance isn't merely a reaction to matter. It is matter itself. According to Einstein, all energy and matter are aspects of the same coin. After all, the universe you see around you is nothing more than a collection of resonating quantum fields. In this view, the universe is A. It's as if the universe's strings start strumming themselves every once in a while, thanks to a concept in quantum physics known as Heisenberg's uncertainty principle. Without getting too bogged down in the specifics, when we're looking at incredibly small objects on the atomic scale, it becomes impossible to know too much about them. You can't know both the size and the composition of these tiny objects. For example, you can't tell where an electron is or which way it's going just by looking at it. This is due to both the limitations of our measuring tools and certain fundamental laws of the cosmos, as outlined by Heisenberg's uncertainty principle. This is due to the fact that electrons are so tiny that any attempt to pinpoint their exact location results in them bouncing off whatever it is you're using to take the reading. The idea that we can't possibly know everything there is to know about subatomic particles gets even stranger when applied to quantum fields. These fields are constantly changing, and according to Heisenberg's uncertainty principle, pairs of particles and antiparticles can appear and disappear at will. The exact reasons for this are unclear, but the universe permits it so long as their existence is brief, according to the rules of uncertainty relations. If particles could simply appear out of thin air, we would have noticed by now. However, experimental evidence discovered by Hendrik Casimir suggests that this could be possible. In his experiment, Casimir placed two conductive metal plates close enough together to limit the number of virtual particles to specific sizes. However, since all types of particles could appear on the outside of the plates, this meant that virtual particles of all sizes could exist between the plates. Based on the theory, the greater the pressure exerted by the virtual particles on the outside of the plate, the more the plates should be forced together. However, in the experiment, the opposite was true. Now, you might be thinking that virtual particles appearing out of nowhere seems to violate the laws of conservation of matter. In such a case, you would be correct. To keep things even, whenever a virtual particle appears, the second particle also appears to pair up with the first. On the one hand, we have matter particles, and on the other, antimatter particles. These two types of particles add up to 0 on our bar chart, making the universe happy. What's more, these fluctuations in the quantum field destroy each other very quickly, so we never have to worry about them. By the way, there's a theory that antimatter is just matter traveling backwards through time, but that's really strange. That is beyond the scope of this discussion. But what is important is that quantum fields are always resonating and canceling each other out. This is why, in general, empty space does not contain any particles at all. Now consider what would happen if you were to silence just a subset of these fields. This is where black holes come in. Black holes are like putting your thumb on the universe's guitar string. Through their event horizons, they dampen certain resonances in the quantum fields while leaving others unaffected. Along a line that ran through space and time, Hawking envisioned a quantum field that would resonate along this line, beginning before the black hole came into existence and continuing into the future after it. In a normal state, quantum fields would resonate freely and cancel each other out. However, when the black hole's event horizon emerged, it altered the curvature of space, and Hawking noticed that some pulses were no longer having their opposite counterparts. After the black hole had formed, he proceeded to travel away from it and noticed resonances that matched the shape of thermal radiation escaping into space. Since energy cannot be created from nothing, the black hole would have to expend some of its energy in the form of radiation. Consequently, each particle of Hawking radiation would coincide with an equal amount of. The black hole's energy dissipates, eventually reducing it to nothing. Similarly, if it were real, Hawking radiation would be like colder cosmic radiation than the background radiation that fills the universe, with a wavelength that matches that of the black hole's event horizon. some of which are the size of solar systems, and would be exceedingly difficult to prove. The only way for us to detect this type of radiation would be if the universe had completely died out and nothing could stop it. Unfortunately, that would likely mean that we wouldn't be here to detect it. Despite these reservations, the math behind Hawking radiation appears to be solid, and scientists have recently made progress in the lab at the Tech in Israel Institute of Technology to prove it. Because measuring a real black hole is so challenging, scientists have come up with an analog that mimics its properties, the sonic black hole. They use the fact that sound travels at a significantly slower rate than light to their advantage, since it's easier to create a medium that moves faster than sound. As a result, any sound waves traveling in the same direction cannot escape the sonic black hole. Interestingly, the same mathematical formulas that worked for gravity-based black holes also applied to sonic black holes. So Hawking radiation should be detectable. Based on the results, researchers observed multiple instances of Hawking radiation after conducting the experiment 97,000 times over 124 days of continuous testing. While this does not prove that Hawking radiation is definitely real for actual black holes, the fact that his calculations work for this sonic analog suggests a strong possibility that he might be onto something. If you were to fall into a black hole, Hawking radiation might be real. Would it be possible to escape from a black hole? Probably not. But if you waited until the universe was nearly at its end, the black hole could emit Hawking radiation until all the mass and energy that comprise your existence was annihilated. Would that be considered an escape? Probably not. So it's probably best not to go in. That's not the only strange thing about black holes. Their existence suggests something quite concerning about our own reality, like when you're strolling on a beach. Here, the chain of events is so obvious that it's funny to have to state it. You made the footprint didn't make you. But what if the reverse was true? What if I told you that on a cosmic scale, the relationship between your foot and the footprint might be less clear than you would intuitively assume, and shockingly, because of black holes and Hawking radiation? There is some evidence to suggest that this could be the case, but before we get into that, let's take a look at a principle called relativity. This particular form of relativity, known as Galilean relativity, was first described by Galileo Galilei in 1632. According to this theory, there is no difference between resting perfectly still and moving at a constant speed. To illustrate this point, let's pretend that there are two rooms, one on a ship and one on land, both of which are soundproof and lack windows. Assume that the sea is calm, so there is no rocking. Can you tell the difference between the two rooms from inside? You would think you could sense movement, but that's not the case. For example, right now you're hurtling through space at 110,000 kilometers per hour because the Earth is orbiting the sun, but if you were sitting at home and watched it, you might have thought it wasn't moving at all. Galileo figured out there wasn't a way to test this. As an example of the dissimilarity between the two possibilities, Galileo discovered that from inside the ship, a drop ball would appear to have fallen straight down, while from a person on land, it would appear to have fallen diagonally. This led him to the conclusion that, in space, there is no way to tell whether a planet is approaching you or if you are moving toward a planet. Both interpretations are equally valid according to relativity. In his equivalence principle, Einstein expanded on this idea by comparing the motion of two rooms, this time to an observation about gravity in a room without windows. Imagine looking out of a train window and seeing another train speed past you, overtaking you. Both trains are moving forward, but the other one is moving faster, so it might appear like you're going backward. Imagine you're in a room suspended in space, subjected to acceleration in the upward direction. Someone straps a rocket to the bottom of the rocket, and if the rocket accelerates at the perfect speed, it will feel exactly like you're in a room on Earth. Assuming you can't stop the rocket from shaking you with its rumbling, it would be impossible to distinguish between the acceleration caused by gravity and the acceleration caused by the rocket. The principle of inertia states that masses do not like to move when left alone and will not stop moving once they have begun moving. Therefore, in order to get a mass to do something different from its current behavior, a new force must be applied. What would it feel like for the man in the room with the rocket to be subjected to gravity, or more accurately, for us on Earth to be propelled upwards by a rocket, given that the Earth is not actually expanding in any way? While it's true that Einstein found the two concepts to be interchangeable, both involved acceleration. There's another kind of acceleration that more accurately describes the workings of gravity than just applying force to an object to make it move like a rocket. Take, for example, the power of changing directions as an acceleration mechanism when you're standing against the ride's wall once it starts to spin. At high speeds, you'll feel a constant force pushing you against the wall, even though the ride itself is moving at a constant speed. This is because at every point along the ride, your mass is attempting to move in a straight line, but the ride's curvature is forcing you to change your direction. The force you're experiencing is the result of the conflict between your inertia, which wants you to stay the same, and the wall, which wants you to change your direction of travel. The difference in acceleration between the. If you imagine the Earth beneath you, speeding you up as you try to slow down, you'll get a good idea of what gravity is. Einstein theorized that matter and energy distort space around them, much like a ball bending a tore rubber sheet. The more mass there is, the more curvature there is, and once space is curved, any object attempting to travel through it would be deflected by. In the words of physicist John Wheeler, matter tells space how to curve. This means that for small masses, the curvature of space would be very slight, but for dense masses, it could become so great that an object too close to it would be unable to escape. These conditions are found near a black hole with its vent horizon. In our original analogy, the footprint and the foot, the curvature of space surrounding a black hole is the footprint, and the black hole tells space how to curve, and once curved, any object moving near it is told how to move. Nothing here is outside our expectations based on day-to-day observations. But when we start to look, it becomes clear how Einstein arrived at conclusions that would have been nearly universally validated by scientists even a century later. So far, nothing seems particularly weird. When we look at Hawking radiation, something peculiar happens. The most crucial thing to remember for our video is that it is non-local, meaning it doesn't come from the black hole itself, but rather from the surrounding space. By this, I don't mean beyond the singularity, but rather from inside the black sphere, which is difficult to define. Regardless, space doesn't exist in this case. The black ball you see here is just the boundary between the inevitability of the black hole and the inescapable. Curves, escapable curves, and the event horizon. No, I don't mean directly on top of it, though that's how some people depict this theory. Instead, the area where this radiation can burst into existence is many times larger than the event horizon itself. In this scenario, one particle would fall inside the other because it's antimatter, and the other would be outside, able to escape. At a distance of billions of kilometers, the event horizons of the largest known black holes can accommodate several solar systems in close proximity. The concept that a photon of radiation can suddenly appear at such a great distance, even in an empty space, is completely absurd. To summarize, Hawking radiation is not so much emanating from the black hole itself as it is from the event horizon itself. The black hole's effect on space can be felt even at great distances from the source of the curvature. However, if this is indeed the case, then the outcome is totally at odds with our expectations. As we shall see shortly, the following sequence of events occurs. Energy escapes the black hole, causing the curvature to decrease due to the principle of conservation of energy. Consequently, the black hole itself shrinks, which is a bizarre phenomenon akin to a shrinking footprint. We are comfortable with the idea of changing mass and curvature, but it works just as well if you go the other way and change the acceleration of spacetime. As a result, it feels very wrong that things can't possibly work that way. However, Einstein hinted that such a thing might indeed be possible in one of his equations. He stated that the curvature of spacetime was proportional to the mass energy of an object. If this is so, then we live in a universe where mass is nothing more than a projection of space curvature, like a shadow cast on a wall by an object. In this case, our hand, interacting with the light. If this analogy holds, you could be forgiven for thinking that we are the hand, and that our mass is what causes the curvature of space around us. But do we really know that it doesn't work that way? On the other hand, could we be nothing more than shadows projected onto the cosmos and brought to life by some deeper, more fundamental process occurring in the curvature of space-time? Despite this, we continue to believe that we are the only thing that truly exists. How can we know this for sure? If we rely solely on our sense of perception, it would be challenging to distinguish between the two possibilities. However, if relativity has taught us anything, it is that when there is no way to discern the difference between them, there is no concrete evidence that Hawking radiation exists, although there have been experiments that suggest it might. Nonetheless, it is intriguing to consider as a theory. Regardless of whether it turns out to be true that reality is a projection, it will not significantly impact your day-to-day experiences. You will continue to think and speculate about the two scenarios. That alone should motivate you to keep doing what you're doing, but it also serves as an example of how delving into the strange warping effects of black holes can lead us to question our own nature. After all, when you ask yourself, am I real? And the answer isn't sure. It's more than a little unsettling. Regardless, black holes impact both our reality and the universe at large. Not only do black holes devour everything in their path and return nothing in return, but they are also the ultimate destroyers of the universe. But what if I told you that these cosmic anomalies could actually be our salvation? Could they hold the key to solving the energy crisis and traveling faster than light? I've come to expect them to do this by tampering with reality itself and by totally contradicting my expectations of physics. Maybe our understanding of black holes has been incorrect up until now. In order to comprehend how a black hole circumvents the usual constraints on faster-than-light travel, in a way that allows us to reap its benefits outside of its event horizon, and how it simultaneously generates nearly infinite energy, we need a deeper understanding of black hole characteristics than what we have covered thus far. To be honest, it's quite challenging to make any definitive statements about black hole features due to the fact that, of the event horizon, we cannot perceive the interior of a black hole. In fact, we can say with some certainty only three things about black holes: their mass, charge, and angular momentum. You may ask how we know these things about black holes, since no light can escape them to tell us about them. The answer is that these three characteristics represent aspects of the black hole that can be perceived outside of it. Scientists can track objects that approach a black hole and predict its charge by seeing how quickly certain objects with a known charge move towards it. This works similarly to how it does around any other charged object. In other words, if a black hole is charged, it will attract objects with different charges and repel objects with the same charge. It's like a giant magnet pushing and pulling on the universe around it. Outside the event horizon sphere, the mass of a black hole is also perceptible. In fact, it is the primary source of the event horizon itself. This is due to the fact that mass produces gravity in a linear fashion, following the same principles as, say, Gauss's law, an electromagnetism theorem with a gravitational analog, which allows one to determine an object's mass by measuring its initial distance from the source and its subsequent acceleration. There are different sizes of black holes, but the smallest, called micro black holes, have a mass that's comparable to that of our moon, or 735 star. Lastly, angular momentum, or spin, can be detected in large mass objects. We'll get into the how in a bit, but for now, let's just accept it as a given that black holes are, without a doubt, extremely massive objects. Incredible as it may seem, all of these masses, ranging from 10 to the power of 22 kg to the mass of the moon, can be contained within a space with a diameter of barely 2 millimeters. To put that in perspective, think of a human hair as being thinner than a black hole, yet with a diameter of 60 kilometers. Stellar black holes, on the other hand, have a mass equal to 10 times that of our sun and a diameter of 60 kilometers. Intermediate black holes, with a mass of 1,000 suns, manage to squeeze all of this into a diameter of 2,000 kilometers, still smaller than Earth. Giant black holes that dwarf us all have masses between 100,000 and 10 billion times that of the Sun and sizes between 0.0001 and 400 astronomical units, where AU is the distance between Earth and the Sun. Other than those three characteristics, there are theoretically no other differences between black holes. In fact, if you replace two black holes in the same room and ensure they had the same mass, charge, and spin, you would not be able to tell them apart. Traveling inside a black hole is theoretically impossible due to the fact that space and time collapse beyond the event horizon. However, there are a few things we can infer must exist inside a black hole, such as the singularity, the black hole itself, and the diameter of the event horizon, which we were discussing earlier. Once again, we don't know what a black hole looks like because light can't penetrate it. In an infinitesimally tiny space, there exists a singularity where the entire mass of the black hole is compressed to an infinite density. In the most basic models of black holes, those without spin, this singularity represents a spinning black hole, which resembles a small ring. Since it is difficult to define spin at a point without volume, current physics around such a black hole becomes mathematically plausible if ideal paths are traveled around it. Encountering one's own past is just one of the strange things that can happen when time travel intersects with singularities. This has troubling implications for causality and leads to paradoxes like the grandfather paradox, which suggests that our current understanding of singularities is flawed. To fully comprehend what happens inside a black hole, we need to successfully combine quantum mechanics with general relativity, which we have not yet accomplished. Perhaps one day we will succeed. It turns out that black hole centers do not contain any singularities. Up to this point, our understanding of black hole interiors has been limited. Whatever is inside a black hole powers our faster-than-light engine, as it spins like most objects in the universe. As we exit the black hole, we make a little fanfare and pass through the event horizon, which cannot be detected locally but could be observed by someone outside the black hole. The passage through the event horizon causes time to slow down to a crawl. From your vantage point, it may appear as though time is flowing normally, but that illusion is short-lived because the universe outside the black hole is moving at a much faster rate than you are. This is the essence of relativity. The photon sphere in the zone immediately outside the event horizon is the only thing that can tell you that you have passed the event horizon. You might be instantly fried as you pass through this point, but it's just outside the horizon, where a photon can enter at the exact right angle and enter a perfect orbit around a black hole, similar to how the moon perfectly orbits the Earth. This incredibly thin zone is called the photon sphere, and it's likely filled with photons from all the millions of years that black holes have existed. The region around a black hole, known as the aerosphere, is where we can most readily detect the spin of the object because, in this zone, motion is inevitable. Because of the curved effect of gravity on objects travel through this region of space, we can observe that mass affects space. However, it is more accurate to say that mass drags on the space around it. As an object moves through space, it takes a small bit of that space with it, and when it collides with another object, as a black hole spins, it causes an effect called frame dragging. Put simply, reality around the black hole starts to spin in an unstoppable whirlpool, much like a real whirlpool. Anything in the ergosphere is pulled in the same way a person moves on a moving walkway. Its frame of reference is being pulled in. The faster the massive object spins, the faster this happens in the aerosphere, and it can reach a speed of. Space is expanding at a rate greater than the speed of light, according to the event horizon. To maintain relative motion relative to an outside observer, one would have to travel at a rate greater than the speed of light in the opposite direction. This, of course, is impossible. However, according to Einstein, nothing can travel faster than the speed of light. In this case, black holes have discovered an intriguing exception to this rule. Objects in one frame of reference can appear to be breaking the light barrier from your point of view if their frame of reference is moving very quickly relative to another. However, if you move close enough to their frame of reference, they will appear to slow down and obey the laws of physics again. This is called frame dragging, and it's a real phenomenon. This measurement frame dragging allows scientists to learn the black hole's spin, but according to Roger Penrose, there may be an exploitative way to use it. If a rocket were sent into this region of the ether sphere, it would speed up as it gets caught in the reality whirlpool. Once it had gained enough speed, it could fire propellant in a way that it pushed itself out of the whirlpool again, but this time at a much faster speed. This method is called the Penrose process, and it could theoretically, you can harness a tremendous amount of energy by traveling to the nearest black hole, which is about 3,000 light years away, and entering its aerosphere with a rocket that can withstand the intense gravitational forces. Although 20% of your rocket's mass may not sound like much, it would produce energy equal to itself times by 299,792,458 squared, according to Einstein's equations. Finding one that isn't encircled by an accretion disk would be ideal, as these objects reach temperatures of millions of degrees as they spin at nearly the speed of light, transforming solids into gas and plasma. All right, so maybe this isn't really practical for us. However, the implications of black holes' frame dragging for faster-than-light travel could provide us with the solution to actually beat the light barrier. Not by traveling faster than light ourselves, but by. We may be out of luck for the time being if this requires the energy of a black hole, but it does provide a fascinating glimpse into the future of space travel. Scientists are already investigating the potential of frame dragging for future travel, but maybe that's for another video. Whatever the case may be, it all serves to emphasize how drastically different our universe is from what we had imagined. You could ever imagine, and here's something else surprising about black holes that you might not have known before. Falling into one is far more difficult than sounds. You would think it would be easy, given that black holes are the ultimate absorbers and the biggest sources of gravity in the universe. However, paradoxically, your intuition is mistaken, and these galactic moos are actually some of the most difficult places to fall into. While Einstein was alive, he held the belief that black holes were impenetrable and could even eject their occupants at near light speed. Logic dictates that such objects would be incredibly inviting, like a progressively steeper slide that promises ever-increasing speeds as one approaches the black hole's center. However, while this is true, it is also incorrect. In fact, one speeds up so dramatically that you'll start to go faster and faster until you're practically touching the speed of light. But in most cases, you won't be getting close to the black hole's core. This isn't some quirk of relativity or some other strange quirk of time. It's something that will be obvious from whatever perspective you're looking at it. If you're still confused, I'll give you an example from the real world. Accretion disk black holes are fundamentally very simple in something called the zero-G paradox. According to the hair theorem, black holes are essentially featureless, like a head with no hair. Black holes typically have simple properties like charge, mass, and spin, and that's about it. Key disks aren't actually required for black holes to exist. In fact, black holes can function just fine without them. However, when mass, like an unfortunate star, gets too close to a black hole's gravitational pull, it can be ripped apart by incredibly powerful forces. The matter is drawn towards the black hole's core, but strangely, it doesn't always go straight into the black hole. Instead, it forms a flat ring that orbits the black hole outside the event horizon. It takes a long time for all of the matter to enter, sometimes 100 to 1,000 million years. So, why doesn't the matter just go into the black hole? It encounters a barrier. Unexpected physical principle called the conservation of momentum was first articulated by mathematician John Wallis in 1670 and later popularized by his contemporary Newton around 100 years later. The basic premise is that any set of moving objects, or their momentum, must always be equal. For example, if a moving particle collides with a stationary one and both bounce back, the total motion of the two particles must be equal. A rocket on a launch pad can only gain momentum by releasing propellant in the opposite direction. However, once the momentum of the air is added to the momentum of the rocket, both the upward and downward components cancel each other out, leaving the rocket with the same net zero momentum as before. This happens just outside our anticipations, because we humans frequently pause and restart our gait as if disobeying this law. However, when you consider all the particles involved, you'll see that this law is always maintained. Without a floor to push against, it will be difficult to move anywhere. The amount of momentum you impart to the floor must equal the amount of momentum you impart to yourself. But in the other direction, you won't notice it because the floor is so much larger than you. What does this have to do with black holes? Well, here's an example involving angular momentum. Picture a ballerina spinning on a single point with her arms outstretched. The particles in her hands have momentum, so they're moving a specific distance at a constant speed. But when she draws her arms in closer to her body, guess what happens? Her spinning speed increases dramatically. This is a classic case of momentum trying to be conserved. When the ballerina tucks her hands in, her spin's faster, and when she stretches them out, her spin's slower. This is because the momentum in the hands is still trying to travel at the same speed it was previously traveling at. But suddenly, because it's close to the body, it's traveling a much smaller distance, but is doing so at the same speed. Consequently, she completes one revolution much faster. Now, picture this on a cosmic scale. In most cases, matter doesn't fall directly into a black hole. Instead, it misses the hole just slightly and begins to spiral inward, entangled in the black hole's gravity. This gives it angular momentum, which causes it to accelerate as it approaches the black hole's center, but on a smaller and smaller orbit, gaining more and more angular spin as it falls, much like a ballerina who wants to go just a little bit further every time. As you go deeper into the black hole, you'll need to spin a bit faster, but unlike the ballerina, this matter is moving at the speed of light. Einstein proved that nothing in the universe can travel faster than the speed of light. So, what happens is that our spinning matter, subjected to massive forces and curvature, eventually hits a wall and can't fall any further because it can't spin faster. The matter in the accretion disk of a black hole can reach temperatures of up to 10 million Kelvin, which is enough to melt anything down to a hot plasma. As you can imagine, this causes friction, which in turn causes the atoms involved to emit more and more radiation as they continue to collide at near light speeds, closer to the event horizon. The process of nuclear fusion, which occurs in the sun, converts only about 7% of mass into energy. Let that sink in for a second. Now, think about how bright a black hole's accretion disk can get. The brightest of these disks, called quasars, can reach brightnesses that exceed 1,000 times the luminosity of the sun. It's like squeezing a lemon. The energy is released as radiation across the universe. The sum of the luminosities of all the stars in the Milky Way. The good news is that some of this momentum starts to be lost with the energy that is escaping, and even more is lost as it is transferred to matter higher up in the accretion disk, where fast-moving particles collide with slower-moving ones, providing them with an additional boost and slowing them down. As a result, the matter starts to lose its angular momentum and eventually falls into the black hole. More momentum can be released into space as it falls. One of the most noticeable aspects of quasars and black holes is their jets. Little is known about their formation and composition, and only a small percentage of black holes with accretion disks have them. However, current theories propose that these jets are generated by magnetic forces generated by the spinning accretion disk or even the black hole's rotational power, which extracts material from the disks and releases it into space. It's probable that as the accretion disks continue to expand, as the disk spins, magnetic fields are created in accordance with Ampere's law by means of all those electrically charged particles in motion. The strength and configuration of these fields are such that, like the rifling on a gun, they confine the particles to a narrow path, and at near relativistic speeds, there is only one possible direction for them to travel, though we don't yet understand why. In the face of immense gravitational and thermal pressure, relativistic jets are like steam escaping from a kettle. When they take off, they travel farther than the galaxies from which they originate and can be millions, if not billions, of light years long. One such jet, with an enticing name, sends X-rays to Earth from 127 billion light years away, though faintly. This is due to the fact that the radiation from these jets is highly concentrated in one direction, a phenomenon called relativistic beaming, also known as the lighthouse effect, occurs when the beam is directed away from us, making it much more difficult to observe. As an example, consider the now famous M87 galaxy. In this case, Hubble clearly detects a relativistic jet, which is moving towards us. It's highly probable that there is another jet, but it's traveling in the opposite direction, so it remains invisible. It's important to note that this energy does not originate directly from the black hole. Rather, the matter and radiation originate from the accretion disk encircling the black hole. Once again, much about these jets is still theoretical. We can see them and watch them move over time, but we don't know what causes them or how they work. What's more, our current understanding of accretion disks doesn't even explain how conservation of momentum is maintained. The exact fate of all that momentum is a mystery. Nevertheless, the immense power at work is indisputable. Einstein may have been mistaken. It is clearly feasible to fall into a black hole, but when some black holes are, we have seen how the effect of a black hole can extend across entire galaxies. But the question remains, how big can a black hole get? The largest black holes have been found to shoot material away from them at relativistic speeds for distances that span galaxies. It's possible to avoid falling into one, but the force of matter, which is millions of degrees hot, pushing out at you as it tries to shed its own momentum makes it not worth it. Black holes is not hard at all. Just look at the centers of big galaxies. These supermassive black holes have been expanding ever since they formed billions of years ago, taking in more and more matter and increasing their mass. The largest of these black holes can be as massive as our Sun, which may come as a surprise to you. On the other hand, when we examine faraway galaxies, we are also peering into the past. The biggest black holes are typically found in galaxies that are billions of light years away. However, if the universe is only 138 billion years old and light takes billions of years to reach us, then the galaxy we're looking at can only be a few billion years old at most. This seems to contradict the idea that supermassive black holes closer to us, which are older, should be more massive because they have had more time to absorb matter. So what's going on? Ton 618 is the most massive supermassive black hole known to science. Its mass is comparable to that of our Milky Way galaxy, but it is located very far away. The light it emits takes 108 billion years to reach Earth, so we are seeing it at a maximum age of 28 billion years. In comparison, our own Milky Way galaxy is about 136 billion years old. Despite this, the supermassive black hole discovered, Sagittarius A star, located at the center of our galaxy, has a mass of only 4 million solar masses. Meanwhile, the Andromeda Galaxy's supermassive black hole is about 200 million solar masses, which is still relatively small. One important consideration is the difficulty of detecting and measuring black holes. This is a relatively new area of research, as technology has only recently enabled us to observe black holes in the past few decades. Even then, we can only see the region immediately surrounding them before the event horizon. We still know very little about black holes in general, and even with the advent of the telescope, it takes a long time to capture images of a single black hole. Most of the faraway black holes we are aware of are quasars, which explain why 618 has erupted into a quasar. Quasars can only remain active for as long as matter continues to fall into them. Otherwise, they revert to dark black holes. According to theories about the accretion disk, the friction in this region is so strong that the AZA accretion disk alone can emit thousands of times more light than all the galaxies put together. In fact, at 618 gigahertz, the disk emits as much light as 40 trillion suns, far more light than the galaxy it is located in. From Earth, we can't even see the galaxy, but quasars, being the brightest objects in the universe, can be seen from great distances, which is why large black holes are. If a galaxy contains a very massive black hole, but it's not a quasar, we won't be able to observe it beyond a certain distance because galaxies are significantly darker than quasars, which is another reason why we don't see them farther away. This phenomenon is known as Malmquist bias, and it occurs when brighter objects farther away appear more numerous than they actually are. This could lead to the suggestion that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. The vast majority of the black holes in our galaxy formed in the early universe, just after the Big Bang. As you may be aware, the universe is constantly expanding, and in those early stages, matter was much denser and more abundant. Quasars, which produce light from extremely dense gas, were more common. As the universe has expanded, gas has been converted into stars, and some of the largest galaxies in the universe have formed from this gas. Some star types eventually transform into neutron stars and black holes. This means they can never be recycled into gas again. As a result, there is less gas available to fall into a supermassive black hole. One theory about the universe's end proposes a scenario called the Big Freeze, in which all the gas in the universe is eventually converted into black holes. At present, we can observe some galaxies where the gas has been exhausted, rendering them incapable of producing new stars. These are referred to as. It is intriguing to note that spiral galaxies still contain gas and dust structures, allowing them to continue star formation. On the other hand, elliptical galaxies seem to be home to the majority of the galaxy's largest supermassive black holes, which would explain why these galaxies are able to produce so many stars. This is because in spiral galaxies, the gas must first lose momentum before it can fall into the galaxy's central supermassive black hole, which would make the supermassive black hole even larger. In elliptical galaxies, this process has already taken place, but in spiral galaxies, it hasn't occurred to the same degree. One possible cause of gas losing angular momentum could be the gravitational pull of nearby galaxies or even galactic collisions. More so, the amount of gas in the universe has decreased over the years, which means that black hole growth has slowed down compared to when the universe was young. This could explain why there isn't a quasar within 500 million light-years of Earth. As the universe ages, things become less chaotic and more distributed, and Since the number of active quasars has diminished, the only quasars, including the largest ones, that we are aware of are those that occurred in the distant past. This begs the question, why are the most massive black holes typically the newest? Well, it could be that we are only able to detect older, brighter quasars, which means that older black holes may also be large, but due to the Malmquist bias, we haven't discovered them just yet. Nonetheless, research into this matter is far from over. As our understanding of the cosmos grows, we will be able to piece together more complex phenomena. One topic that has received a lot of attention recently is black holes, which are fascinating regions of space-time with extremely high curvature. These regions display features and phenomena that defy our classical physical intuition. However, there are other ways that space-time can display its beautiful curves, theoretically speaking. White holes, which are similarly curved regions of space-time, get their name from the fact that they are very different from black holes. Wormholes, a different type of space-time, can link black holes and white holes, creating a sort of limbo zone between parallel universes. If the idea of space travel through wormholes sounds like something out of a science fiction novel, I can understand why. After all, these regions are theoretically feasible. White holes and wormholes may not exist in reality, but a century ago, black holes were the only ones in the cosmos. Today, we believe there are billions of them waiting to be seen by our telescopes. In this video, I'm Alex Mullen, and I hope to answer 3 questions. What are these other holes that could exist in space-time? Should we be hopeful that they are more than just science fiction? And what would they look like if they were real? I want to begin with a simple analogy. When I ask you to imagine a cone, you might picture something pointed up like a traffic cone or something pointed down like an ice cream cone. These are the 2 most common types of space-time that can result from extreme curvature. I think the possibilities we'll explore today will bend your mind just as much as they warp the fabric of the universe around them. What we perceive as cones in the physical world are actually fragments of the complete mathematical cone. Similarly, when we attempt to graph the most general mathematical equation for a cone, what we obtain resembles a mathematical double-ended cone. This is because, as you can see, a mathematical cone consists of an upward-pointing half and a downward-pointing half, joined at their tips. Black holes are the remnants of supermassive stars that collapsed due to their immense gravity. Once a black hole forms, it is permanently cut off from the rest of the universe by a spherical barrier called the event horizon. Anything can fall into a black hole, but not even light can escape. This structure of space-time is neatly summarized in a diagram that physicists use to represent it, a Penrose diagram. The main feature of this diagram is that light does not travel. Region 1 represents the regular universe, which includes the original star before it became a black hole, as well as everything outside of it from the infinite past to the infinite future. Region 2, separated from the rest of the universe by its event horizon, is the black hole itself. Light can easily enter Region 2, but it will inevitably hit a singularity instead of escaping. Just like in the real world, ordinary matter moves at a slower rate than light. As a result, it can only ascend in this diagram at angles steeper than 45 degrees. The unique thing about this Penrose diagram is that it explains how black holes form at a specific point in time when stars collapse in on themselves. Back then, there was no such thing as an event horizon or black hole. Light could travel far faster than in our modern world. In our everyday lives, it's just a small part of the complete mathematical picture of black holes in general relativity. Think of it as the ice cream cone of black hole diagrams. Now, what if we were to imagine an ideal black hole with an endless past, erasing all evidence of star collapse and the rest of the physical universe? What would the black hole equivalent of the complete mathematical picture look like? It could be an extension of our original Penrose diagram, but this wouldn't be the case. Region 2 still represents our regular universe, while Region 3 is a black hole with an inevitable future singularity. However, the maths also describe something in Region 3, which looks like the inverse of a black hole. Instead of a future singularity, Region 3 has one in its past. If you plot the motion of light rays at 45 degrees angles, you'll see that light can easily exit Region 3, but it can never enter this type of region, what we would call a white hole, the space-time equivalent of a traffic cone. But that's not all. If you extend your view beyond the white hole, you'll notice a region of space-time called Region 4 that has identical connections to the regular universe's black holes and white holes. This patch is a parallel universe, isolated from the universe in Region 1, because not even light can travel between the two regions. The result is that the same equation describes. The regular universe is described by black holes, which also describe parallel universes and white holes. This doesn't mean that every black hole is attached to a white hole, but just like cones, the real universe can contain piecemeal solutions. What this does mean is that white holes, whether they're less common than black holes or not connected to our universe at all, are just as scientifically significant. In keeping with the laws of physics, let's pretend for a moment that ice cream cones are still very popular, while traffic cones are becoming harder to make and eventually disappear. This is basically the current state of white holes. They make perfect sense, but it's possible that any white holes that have existed before were unstable and eventually disappeared. If you're wondering if there could be any, you aren't the only one. In a few minutes, we'll be discussing the tiniest white holes that have ever existed. But before we get to that, I want to make sure we're not leaving anyone hanging. I told you about wormholes and connected parallel universes. Now get ready for a trip to a whole new dimension in distorted space-time. According to the node theorem, a black hole can contain up to 3. The Penrose diagram I showed you only depicted the most basic type of black hole, one that was electrically neutral and completely stationary. However, diagrams for charged or spinning black holes are far more complicated and intriguing. These types of black holes change our view of singularities and give birth to new and interesting regions of space-time. Let's take a look at a spinning black holes diagram instead of 4 different parts of space-time. There are now 8 different kinds of regions that repeat themselves in an endless number of universes. The first 4 are the same as before: the regular universe, the black hole, the white hole, and the parallel universe. However, since black holes spin, their geometry no longer has an inevitable singularity in the future, and white holes also lose the singularity that was there in the past. So, what happens when you cross the event horizon of a spinning black hole? Black hole at first, you'll be pulled in the same direction you would expect, into its center. However, after you cross a certain threshold, called the inner horizon, the geometry of space-time begins to warp, preventing you from falling any further. In the innermost regions, marked 5 and 7, you can float freely either towards or away from the black hole center. Here in the innermost regions of a curved, rotating space-time, you could even touch the singularity, though I wouldn't recommend it. You have entered a wormhole and would have been able to boast about your awesome space adventures if it weren't for the fact that you are now eternally cut off from everyone in Region 1. Now you're at a crossroads, though. One path would take you to Region 6 or 8 in the diagram by continuing inward and circling the singularity, which looks more like a ring than a point, but there's a good chance that the existence of this path is more of a problem with general relativity's predictions than an accurate depiction of reality. Even a single loop around the singularity can cause causal paradoxes where you end up in your own past. To avoid these, it's safer to turn around and move outward. If you were to cross back into the inner horizon from where you just emerged, you'd enter Region 3, a white hole. From there, you'd be transported to a new universe with a structure identical to the one you originated from. Began in, but alas, there will be no one to greet you when you arrive. In fact, your home universe will have lived through an endless amount of time, and you will be experiencing a completely different version of the future. All right, let's return to reality. As entertaining as the wormhole journey may have been in theory, it's safe to say that you wouldn't have survived its practical implementation. Honestly, there's a good chance that the wormhole would collapse the moment you disturb space-time. So how much of a spinning black holes with event horizons and this mathematical structure seem to be found all over the cosmos, but little is known about their interior physics. There are two key reasons why the physics of real black holes might differ from what the Penrose diagram suggests. Firstly, when black holes form from the violent collapse of massive stars, some of the assumptions used to create the diagram are broken, such as the idea that the black hole has existed forever or the surrounding cosmos is perfectly symmetrical and devoid of any randomly falling humans. And secondly, the theory of general relativity that was employed to create the Penrose diagram may only be roughly right, failing to account for the extremely curved space-time near the singularity. Consequently, there is a strong possibility that certain predictions made by the diagram, particularly those concerning singularities and time travel paradoxes, are not actually characteristics of such a curvy space-time, but rather arise from the. There's been some recent interest in the idea that white holes form when black holes die. This isn't some superstitious tale about reincarnation or voodoo. Rather, it's an honest effort to understand the complete life cycle of black holes with mathematical evidence. After all, even a single black hole can leave behind a trail of mysterious phenomena that could lead us to their origin. A black hole in a vacuum will slowly lose mass as it continues to emit Hawking radiation. But once it reaches a very small mass, about 20 micrograms, no amount of predictive power can help us understand what lies ahead, at least not without a comprehensive theory of quantum gravity. This is where loop quantum gravity comes in, a proposed connection between gravity and quantum mechanics, in which space is composed of discrete loops, or the equations of loop quantum. According to general relativity, a black hole so small that it could not possibly continue to shrink any smaller than the Planck mass would likely undergo a quantum tunnel and transform into a white hole, which it would then release into space over a long period of time. Despite its small size and light weight, this white hole could hold a tremendous amount of entropy due to the fact that its internal geometry would have been compressed into a thin tube with an extremely large volume. This video will come to a close, but before I go, I want to leave you with one last thought. According to general relativity, our entire universe is predicted to have had a merger at some point in the past. If this proves to be true, then any data that falls into a black hole can be retrieved in the far future, solving a theoretical physics problem called the information paradox. Singularity in its past, specifically 14 billion years ago at the Big Bang. In this way, the universe functions similarly to an uncharged stationary white hole. However, according to loop quantum gravity, white holes can be created when black holes collapse. Could this also apply to the creation of our universe? As far-fetched as it sounds, it is possible that our expanding universe was born from the ashes of an older contracting spacetime. We have so many theories about what might have happened during this transition that it would take a new video to cover them all. So if you're interested in hearing more about the possibility that the Big Bang was really a big bounce, leave a comment below. Who knows? Maybe the cosmos has more surprises in store for us. In any case, we appreciate you taking the time to watch, and we thank you, astronauts, for your consistent and sustainable support on Patreon, which allowed us to make this video. Join our community by clicking the link below. If you're interested in seeing more videos like this, we'd love to have you. Once you're a member, you'll have access to ad-free viewing, your name will be added to the credits, and you can ask our team questions. Join now, and we'll see you next time.